Hello and welcome back to the course on deep learning. Today we've got a very exciting tutorial ahead. We're talking about long short-term memory, or LSTMs for short. So let's get started. It's actually going to be quite a saturated tutorial, so we've got our own little plan of attack for today. Today we've got to first of all look at a bit of history, so where it came from, what was the main idea behind it, why people invented it. Then we're going to be talking about the LSTM architecture. That's going to be the bulk of our tutorial today, so be prepared for that. And then we're going to have an example walkthrough. Hopefully we'll have enough time for that as well. All right, so let's get started. Here we've got a problem which we identified in the previous tutorials. We talked about the vanishing gradient problem. So in short, what happens is as we propagate the error through the network, it has to go through the unraveled temporal loop. And as it does that, it goes through these layers of neurons which are connected to themselves, these hidden layers which are connected to themselves, and they're connected by the means of a weight called the WREC, or W recurrent weight. And because this weight is applied many times on top of itself, that causes the gradient to decline rapidly, meaning that the weights of the layers on the very far left are updated much slower than the weights of the layers on the far right. And this creates a domino effect because the weights of the far left layers are very important because they dictate the outputs of those layers, which are the inputs to the far right layers, and therefore the whole training of the network suffers, and that is called the problem of the vanishing gradient. And as a rule of thumb, we could see here that if WREC is small, then we have vanishing gradient. If WREC is large, then we have exploding gradient. So now, how do you solve this problem? We talked about a couple of possible solutions. We talked about clipping the gradient or penalizing the gradient for exploding gradients. We talked about smartly selecting the weights or the echo state networks, which we didn't go into detail on for the vanishing gradient. And also we talked about the LSTMs for the vanishing gradient. Just if you separate yourself from all of this information on all this theory and knowledge, how would you solve a problem like this? What's the easiest and fastest solution to this? So if we have WREC is, in simple terms, less than 1, then we have vanishing gradient. If we have WREC greater than 1, we've got exploding gradient. What's the first thing that comes to mind to solve this problem? Well, the first thing that comes to mind is to make WREC equal 1. And that's exactly what was done in the LSTMs. This is a very simplified explanation, and there's definitely more to it than just WREC equals 1. But in general, that's the idea, and that's all it took. And when I saw this for the first time, I was so excited that the solution is so simple. It's really a genius solution, and that completely gets rid of the vanishing gradient problem. And who are the people behind this? Here are two gentlemen. We've already talked about Sepp Hochreiter, and the second person is Jürgen Schmidhuber, who was his supervisor during Sepp's research or PhD. And yeah, so basically they wrote a paper in 1997 about LSTMs, and that's when LSTMs were introduced to the world for the first time. Very exciting topic. So let's have a look at what they actually are. So we've got a recurrent neural network right here, unraveled temporal loop. This is what it looks like if you dig in inside the recurrent neural network. And right here, I wanted to do a quick shout out to Christopher Olah. So here is his blog right here. Very well written blog, amazing images, as you can see, and we're going to be using the images from this blog in our explanation here. So thank you very much to Christopher for making this publicly available and allowing the use of his images in other works. So we'll definitely reference this at the end of today's tutorial. And going back to our presentation, so here we've got the recurrent neural network. And this is what it looks like inside, and this is where the problem lies. So this operation that happens here is actually a neural network layer operation, as we'll see further down. But simply put, as you have outputs coming into your module, into this module, this operation is applied, and then goes into the next module, operation is applied, and so on. So as you apply this operation, when you back propagate, it goes through all of this, and that's where the weights are applied. That's where the wrec is sitting. As that weight is applied, as it's applied, the gradient vanishes, and vanishes, and that means that the weights cannot be updated properly or fast enough to train the network properly. And so the further away you try to look, the more problems you have and the more of the vanishing gradient you have. This is the standard RNN, and this is what the LSTM version looks like. And I know you might be thinking that, whoa, this is super complex. There's so much going on here, and indeed it is a bit more complex than the standard RNN, but check this out. This is how LSTMs are normally displayed in literature and in papers and so on. So definitely, this is the same thing as you saw before, but it's just a much more convoluted explanation or representation. So definitely this option is better, and we're going to stick with this one. And more so, it looks difficult now, but the goal is that by the end of this tutorial you are completely comfortable with what's going on here, and I think that's pretty exciting. That this, even though this may seem a bit complex now, towards the end of the tutorial, hopefully you'll be able to navigate LSTMs quite well. And so before we go deep into what's going on here, I wanted to highlight the main point. So remember we said wrec equals 1. Well, that's this line over here, that pipeline at the top. As you can see, there's not much going on here. There's only like 2 point-wise operations, as we'll understand further down, and there's no complex neural network layered operations. They're all brought out to this part, and this is the essence. If you're going to take away one thing from today's tutorial, then this is that LSTMs have a memory cell. It's called the memory cell. I call it a memory pipeline, which just goes through time, and this is us going through time, and it can very freely flow through time. Sometimes it might be removed and erased. Sometimes things might be added into it, but that's pretty much it. Otherwise, it flows through times freely, and therefore, when you back propagate through these LSTMs, you don't have that problem of your vanishing gradient. That's the essence of LSTMs. All right, so now let's dig in a bit more detail. So we're going to replace these modules on the left and the right with something more simple. Just going to replace them with these representations. So C stands for memory, memory cell, I guess. H is your output. So you can see there's your output going out into the world, and here you got your output going into the next module, into the next block, and then here you've got your input xt. So basically this is the output from the previous module, which also went into the world, but also is coming here. So there we go. So an LSTM module takes in 3 inputs and has 2 outputs. So CT and HT, because these are the same. And an important thing to understand and remember is that everything here is a vector. So all of these this is not just one neuron, not just one value. There are lots and lots and lots of values here hiding behind this letter xt, and here as well, and here as well, and everywhere. These are all layers. So just remember that, and we're going to reference them as vectors because that's pretty much the same thing, just lots of different values in one vector. Remember that, and that will make it will allow you not to go down the wrong path in the intuitive understanding of this. Just remember that these are all vectors. And let's go through the legend. So we've got vector transfers. So any line here is a vector being transferred or kind of moving around in this architecture. And yeah, so that's just kind of to reiterate that it is a vector. Then we've got a concatenation here. So here you can see that there's 2 lines combining into one. And important to understand that this is done here just to save space and make it less convoluted than it possibly could be. But the best way to imagine it is that these 2 lines are running in parallel, that you're not actually combining. Concatenation means that you're combining these 2 vectors on top of each other, but I think it's even easier to understand if you just think of it as in there are two pipes running here, but they're running parallel to each other. So you've got one pipe and then it goes here and the second pipe goes here. Then these same pipes go here and then they attach to that. So basically you have two pipes running in parallel feeding into these neural network layer operations. Then you've got copy. So where do we have copy? We have copy here. The memory is copied, goes straight ahead and just copied over here. Then this output is copied over here. Then you've got pointwise operations. Now we get to the interesting stuff. So you've got a couple of pointwise operations here. That's 5 of them. And the first thing we're going to talk about these ones, the X's. The X's are valves, and they all have names. This is the forget valve, the memory valve, and the output valve. And in literature, you will see like letters F, V, and O in the actual formulas representing these valves. And so a valve looks like this. in plumbing, a valve looks like this, and we're going to kind of think of it that way as well. So you've got water or basically something flowing through, and then you can either close it or you can open it or you can close it to some extent. Same thing here. So you've got the forget valve is basically controlled by this layer operation, and we'll talk about that in a second. And based on the output of that, based on the decision made here, this valve is either closed or open. So if it's open, memory flows through freely. If it's closed, then memory is cut off, and therefore it's not transferred further, and then new memory just will be added here probably based on the results here. Then you've got the memory valve, which again is controlled by a sigma. Sigma stands for the sigmoid activation function. That means that that's the activation function used in these layer operations. And as the decision is made here, this value, which is another layer operation, which we'll get to in a second, is either added to the memory or is somewhat added to the memory or is not added to the memory, depending on the value that is decided in this valve. And then again, another valve controlled by a sigmoid. As you remember, sigmoid, why we're using sigmoids, because they're from 0 to 1. And therefore 0 stands for no memory, nothing goes through, 1 stands for something goes through. And then here you've got the valve, which is the forget valve. Same thing, not the forget valve, this is the output valve. And we'll get to that in a second. We're pretty much already going through the whole network already. And then we've got the T-shaped kind of like pipe or T-shaped joint. And I'll show you where that is. That is over here. So where you have memory going through, and then you can add additional memory. So if we go back, you've got memory flowing through this joint, and maybe some additional memory will be added into it. Maybe not, depending on the valve. And that's pretty much it. You've got the tangent operation here. That's more kind of like mathematical behind it, why you want it between -1 and 1. We won't get into details on that, but that's another pointwise operation here you have. And you've got the neural network layer operations over here. That's their representation. So basically, just think of them as you've got instead of pointwise like element by element of a vector. If you want to multiply a vector by 0, you multiply every element by 0 or by 1 or by a certain amount. Kind of think of it in that way. That's a very simplistic way to think about these pointwise operations. Whereas these ones are a bit more complex. You've got a layer coming in, and then you got a layer coming out, or like a layer, because again, everything here is a vector, so you've got a layer of these sigmoids coming out, controlling the valve for each one of these elements in the vector of memory. So there's not just one sigmoid, there's many different, and that's why you've got a whole layer coming in, and then you've got a layer coming out. These are layer operations, so just remember that. And yeah, so we're ready to look into this in step by step, and it's going to be pretty simple because we've discussed everything already in terms of how it works. So we've got a new value coming in, you've got memory, so you've got not memory, you've got a value coming from the previous node, and together they are combined to decide whether this valve should go ahead or should be closed or should be opened, or somewhat closed or opened. Then you've got these two again combined together, or not combined, like they flow in parallel, and then they're combined in here or in this operation. And basically it's not just them combined, it's like there's lots of layers here, lots of layers here, like lots of neurons here, lots of neurons here, and then all of that is basically in one layer operation is used to decide what value we're going to pass through, and then also if that value is going to pass through or not, and to what extent. Then here we've got the memory flowing through. We've got the forget valve, if it's closed or open. We've got memory valve, closed or open, and we're adding in some memory possibly if we want to update. So basically we can let this whole memory flow through, then keep this one closed, keep this one open, the memory won't change. Keep this one, or we can keep this one closed and keep this one open, then we can update the memory completely. And here finally we've got these two values combined to decide what part of the memory pipeline is going to be output, is going to become output of this module. Is it going to go fully as the output or to some extent, and so on. So again, these decide that. So that's how it all works. Pretty straightforward architecture. Let's have a look at a specific example to understand this a bit better. So the example we talked about, I'm a boy who likes to learn, isem který rád učit, in translation to Czech. If this were girl, then here would be isem holka která ráda učit, meaning that these two words, not just this word would change, but also it would affect these two words. So different to in Czech rather than in English. So these words are affected by the gender of the subject. And therefore, in our LSTM, we might want to store the subject, boy in this case, in the memory. So for instance, let's say boy is stored here, and then it's just flowing through freely, and nothing is changing. Like if our new information doesn't tell us that there's a new subject, we just have boy flowing through freely and keeps flowing like that. If, for instance, we have a new subject, we have girl, or we have a name like Amanda or something else, and we understand that we've got a new subject, then we'll let this valve, we'll close this valve, we'll say, destroy the memory that we had, then open this valve, put in new memory, and then put the name here, put the subject. We won't just put in the gender, we won't just put in like female, we'll actually put the whole, as much information as we can. For instance, this could be the architecture. It doesn't have to be like this, but as an example, we could put in, for instance, girl now into this pipeline. And why would we do that? Well, because then from that, we can extract different elements of information. We can extract that it's female. We can extract that it's singular, right? So not just that there's additional information, the word girl, that it's singular. We can extract more information. We can extract that the word girl, for instance, has 4 letters, or that it was capitalized or wasn't capitalized. Just as these are all very, very intuitive examples. It doesn't have to work this way, but this is how it could work. And so then we have the word girl in here. And so that's how this valve works and this valve works. And so what this valve does is it extracts certain information from what you have in the memory. So for instance, if we have now girl in here, and for the purposes of the next word or next sentence that's coming up, you might need to know, like we saw, you need to know the gender. So then this valve will facilitate the extraction of the gender, and that will go as an input into your next module, and it'll help the next module, like it'll be here, decide how to deal with the information that's coming its way, how to put it into the correct form for the female gender, for example. And so that's how the output valve works and what it does. So there we go. That's how the long short term memory works, and I hope this was quite an intuitive explanation, and now you have a bit of a better understanding what LSTMs are like. In terms of additional reading, you could definitely reference the original paper by our 2 authors who created LSTMs. Alternatively, if you don't want to get that deep into mathematics and into the technical stuff, there's the great blog by Christopher Ola, which we've already mentioned. A great explanation of LSTMs. Highly recommend to check it out. There's a bit of mathematics, not too heavy. And there's another blog by Shi Yan, Understanding LSTM and its diagrams. Diagrams are a bit more in-depth, so they're a bit more, there's a bit more less space saving, but diagrams are a bit more in-depth, might be easier to understand in some cases. No mathematics whatsoever, just plain intuition. So also highly recommend this blog to check it out if you would like to get a bit of additional information on LSTMs. And on that note, I hope you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy deep learning.